So here we go on unit number 2, lesson D, applying Newton's laws number 2. This time we're going to look at friction and drag. Now drag really is just a kind of friction. It's just a friction that's brought about by fluids, liquids and gases. Friction is a force that acts in the opposite direction of motion. So if I'm pushing on a box up a incline, my frictional force will push in the opposite direction. And there's two types of friction that we're going to be focused on right now: static friction and kinetic friction. So imagine I've got a jug of juice sitting here, and I begin to push on that jug of juice, or if it's anything, right? You start pushing on something, and when a small force is applied, that object stays there in equilibrium because that static friction force is equal but opposite to that applied force. So imagine you're just pushing an object, trying to slide it along the floor. You have to push, and then it suddenly starts moving. Okay, and when it begins to move, you can often feel this. You can get up and try it right now, sliding something fairly massive across a room. Okay, you can push, and then it sort of gives and starts sliding. What's happening there is, as you're pushing, you are having to increase the force with which you're pushing as the friction, the static friction from that object pushes back, it wants to hold that object in place. Okay, finally you push hard enough to counteract that static friction. That static friction reaches a threshold point, and you push it further, and you are able to push it. So this frictional force depends on the normal force of the object and the nature of the surfaces in contact. With normal force, right, as we increase the normal force on an object, we will increase the amount of static friction it has. All right. Imagine you're pushing a table across a room, and then you have somebody sit on the table, right? Well, you've increased the normal force on the table, so you're going to increase the amount of push you have to provide it, thereby increasing the amount of friction. We can also look at the nature of the surfaces in contact. Okay, each surface, all materials they're not perfectly smooth, right? When we begin to look at things at the microscopic level, there's these little pits and valleys throughout those surfaces, and they snag up on each other. All right, and so friction will arise because no surface is completely smooth. Okay, we can reduce friction by getting smoother surfaces, but we can't ever totally get rid of it. Another reason for friction is that microscopically our surfaces will create, place an object on a surface, and it'll create kind of an indent in the molecules that make up that surface. So here's a little object here. This is greatly exaggerated, of course. And so if we look right in here, right, it's like a little, if we were to try to push on this back here, right, we've got ourselves a little hill, a little lip we got to get over in order to begin that push. So there's three reasons why we have friction. It's because of the normal force, the nature of the surfaces in contact, and that tiny indentation that happens microscopically when we place an object on a surface. Now we can characterize the surfaces together by something called the coefficient of friction. Okay, every object has a certain coefficient of friction, every surface. Okay, so this coefficient of friction is really just a ratio of forces. We can have what's called the coefficient of static friction, and we can have the coefficient of kinetic friction. So the coefficient of static friction is the ratio of the maximum value of the force of static friction to the normal force. And the coefficient of kinetic friction is the ratio of the force of kinetic friction to the normal force. And what we're going to find is that kinetic friction is always less than static friction. Okay, and we saw that with that juice, right? When we begin to slide something, it's easier to keep it sliding than it is to start something sliding. Okay. So we can take our two expressions for those coefficients of friction and generalize them and come up with a single expression for frictional forces right here. So the force of friction is equal to the coefficient of friction times the normal force. Your equation sheet reports that this relationship this way right here, where the force of friction is less than or equal to the coefficient of friction times the normal force. It's really important to understand too that friction is independent of the surface area of contact. Okay, the force of friction depends only on the normal force and the surface materials. Now if we take a look at, say, a graph of friction versus applied force, okay, as you begin to push on something, say we've got a box over here and we've got a person that there's a person going to push that box this direction, okay. As they begin to push that box, their force increases linearly because that static friction matches that applied force. At some point, get to a threshold of motion where suddenly this is where we get that little slip and we begin to have this constant kinetic friction here. So what this is saying is static friction will increase until we get to that threshold point. Then kinetic friction continues on at a constant. Okay, and this is that section of the graph blown up there. Okay. All right. So static friction keeps an object from moving, whereas kinetic friction is directed opposite the direction of motion. So if an object is not moving, we'll be working with kinetic or static friction, and in those cases, if we're dealing with static friction, that's going to be an equilibrium situation with no net force and no acceleration. If we've got kinetic friction going on, then there is still an equilibrium situation. There could be an equilibrium situation, but we've got motion. Or if our push then becomes greater than our kinetic friction, we'll get an acceleration. Now, different materials have different coefficients of friction, and here's a table of various coefficients of friction. It should be there in your reading packet. So let's take a look at an example, the force to push a box. So we got Carol pushes a 10 kilogram wood box across a wood floor at a steady speed of 2 meters per second. We want to know how much force does she exert on the box. So with this box then has a weight force, a normal force, the force from her push, and frictional force down here, and it's going to be a kinetic friction because we're sliding along the floor. Okay, the box is a mass then of 10 kilograms, and we're moving with a constant velocity of 2 meters per second. So when we go to analyze these forces, right, we're gonna notice that we have no motion at all in our y direction, and none of our forces are acting at an angle. That's all horizontal and vertical. So we're going to look at just our x direction here, and so we end up with an expression here. So the force of our push then, and we've got our frictional force, and our expression for that frictional force will be the coefficient of kinetic friction times the normal force is equal to 0. So now we have to think, well, we've got the normal force sitting here. So, wow, now we do kind of have to look in our y direction, don't we? We've got now a force of our push minus our friction, or coefficient of friction, times our normal force, which is equal to our weight. Okay? Well, we learned previously that we have an expression for weight that we need to look at too. So now we've got force of our push times our coefficient of kinetic friction times mg here. Okay? So this now gives us our full expression then for what's happening in that x direction. So then we can begin to plug in numbers, substitute in numbers, and solve. So when we look at that, right, well, this 0.2 is our coefficient of friction for wood on wood, coefficient of kinetic friction for wood on wood. So this is that's where that comes from. It's from the table in the previous slide. And we solve this, and we end up with 19.6 newtons. That's how hard she's pushing. Okay, so let's look at another example here. We've got a 50 kilogram steel file cabinet in the back of a dump truck. The truck's bed is also made of steel, and it's slowly tilted. What is the size of the static friction force on the cabinet when the bed's tilted at 20 degrees? Okay, so here's our dump truck with our file cabinet in the back of it. It's tilted at a 20-degree angle, so that would be our angle of slope there. And because we're tilted, we also tilt our coordinate plane. So let's take a look at the forces acting on this file cabinet on this dump truck. The file cabinet has a weight force which points straight down. Normal force, which points perpendicular to the surface. And it's got this static friction force opposing the direction of motion that it would slide if it were to slide. Now, whenever we have an angle, a sloped surface, right, the angle of that slope is going to be the same angle in our free body diagram as this angle right here. Okay, if we were to do an analysis, we would see, if we were to draw a triangle here and here, we would see that both of those are similar triangles. That's this angle here is the same as this angle here. Okay. So because this weight force is acting straight down, we have an angle on our surface. So some of that weight force gets split up, right? Some of it points opposite the direction of the normal force, and some of it points down the ramp. Our file cabinet's not sliding, so what that tells us is that this component of that weight, FGX we'll call it, is going to be equal to our frictional force, our static friction force up here. And FGY, the Y component of our weight force, will be equal to the normal force. So we can now begin to analyze these forces. So in our X direction, we have the X component of the weight, we have that frictional force. The X component of the weight acts down the ramp, which is a positive direction. The frictional force acts up the ramp, the negative direction. In the Y direction, then, we have a normal force and the Y component of the weight. Both of these, we're not moving, so we have static friction. So our net force in each direction is equal to 0. So then our expression for our weight in the X direction is going to be mg sine theta, because the X component is going to be opposite that angle, minus our static friction force. So our file cabinet has a mass of 50 kilograms, G's 9.8, our angle's 20, and that will equal then our static friction force. And solving that gives us a frictional force of 167.6 newtons. Okay, so now let's talk about drag. Okay, drag is it's a frictional force that's brought about by fluids. Fluids are gases or liquids. So, like surface friction, okay, drag is opposite in direction to the direction of motion, or opposite in direction to the velocity. It increases in magnitude as the object's speed increases. So for this car moving down the road here, we got a thrust force in one direction, drag opposes it this way. For an object in free fall, right, when an object is in free fall, the drag force from air will gradually increase until it is equal to the force of gravity pulling the ball down, pulling whatever object is falling. Okay. At this point, we reach what is called terminal velocity. So once an object has reached terminal velocity, it'll continue falling at that speed until it hits the ground. In liquids, the drag forces are proportional to the cross-sectional area of the object, its speed, and the viscosity, or the resistance to flow of that fluid. Okay, so everything that we've done so far, we've looked at the forces acting on just one object. So for the next video, what we're going to do is look at interacting objects when we have two or more objects interacting and the forces between them. See you then.